So welcome to lecture 22 of MCS 472. So there are a lot of twos in this lecture. Today we will introduce mathematical modeling with ordinary differential equations. So it will be what is often called the scientific method, which we will illustrate on 3 problems. And the lecture will end with 2 examples of mechanical problems. So all the computations in this lecture are symbolic. The emphasis is on the modeling, on the derivation of the differential equations. The models are sufficiently simple that they can also be solved and interpreted completely symbolically. Okay, so what is our first problem? So we look at a model of slowing down and rather in a stressful environment. So we are in a submarine at 40 knots, and all of a sudden we have a mechanical problem. After 1 minute, our speed has dropped by 10 knots from 40 to 30 knots. Now, how long do we have to make repairs before the forward motion falls below 2 knots? So that's a pressing problem, and we probably need to solve this. This lecture will last more than 45 minutes, but we will have to come up with a very quick answer to that. The second problem is a problem now that spring is arriving, is a little bit less scary. So it's a very cold winter's evening, and those evenings are now past us. It's beginning of March. So the outside temperature is well below freezing. Our furnace fails, and we see that after 1 hour, the temperature have dropped by 5 degrees Fahrenheit. Now, how much time? It's in the evening, it's late in the evening. We have, we're living in a good city where there is emergency service, but suppose that would not be available or too expensive. How long does it take till it starts freezing inside? So that's the second problem. The third problem is more in the abstract. Predict the future population of a developed country. By that I mean that we actually do not foresee catastrophes happening. Okay, so this is an overview of the problems that we will solve. Now there are 2 examples from mechanics. So consider a pendulum in the plane. So we have as input parameters the mass and the length of a rod that attaches the mass. So in equilibrium position, the angle is 0, and we have one variable that measures how far the pendulum, the mass, is from its stable equilibrium position, which means just a vertical suspended position when there is no motion at all. The second example considers a sliding mass spring. So we have a mass that slides on a horizontal table, and that mass is restrained by a spring. So we have the force from the mass, and then you have the restoring force. So this pendulum module and the sliding mass problem will lead to simple second order equations. So the sliding mass spring is actually quite equivalent to the pendulum problem, but the setup makes it kind of convenient for traffic modeling. So that's then a problem that we will consider in a later lecture. Okay, so everything will be symbolic in this lecture. So by way of introduction, let us consider one method for solving an ordinary differential equation. So here we see an example of an ordinary differential equation where we have a left-hand side, which is the derivative of a function y depending on x. And the right-hand side is kind of specific, so it can be decomposed as a product of two functions. One function depends on the independent variable only, so we have the f depending on x, whereas the second function, the g, depends on y. And for differential equations of this type, we can apply the separation of variables. And it is the solution. So provided that we actually have uniqueness, so we have a first order differential equation, so only a first derivative at the left here. This first order derivative, this first order differential equation is fully specified if we give it an initial condition. So we have for some x naught, we have a value y naught. So this initial value problem has a unique solution. So let's demonstrate this on a very simple example. So here the f of x is x, the g of y is 1 over y. So we consider this problem then with the initial condition that at y equals y at 3, we have the value 5. So the x naught is 3, the y naught is 5 of the previous slide. So there is a Jupyter notebook posted with this lecture that contains all the computations. So we do this with a Julia kernel, and we will be using SymPy. So essentially everything can also be done with Python. So to set up the differential equation, we define the symbol for the independent variable x, and our y has to be a function, a symbolic function. So we can then evaluate the symbolic function, the symbol y, at a symbol. So that's very necessary when we formulate the differential equation, when we apply the diff method to y. So we have to use the EQ construction to formulate the equation. So the first argument of EQ is the left side, the second argument is the right side. So using the equal symbol doesn't really work that well here because the equal is reserved for the assignment. So I will give the prompt. So this is copied and pasted from the output cell in the Jupyter notebook. So the first three statements here indicate that these are the commands that appear in the code cells of a Jupyter notebook. But it would also work in an interactive Julia session. So actually the slides have been made from a Jupyter notebook. So to solve this ODE, we would apply solve, but it's a differential equation, so therefore we do desolve, and there's only one single argument. Desolve is clever enough to figure out what is the function we are solving for. So there we then see we obtain a symbolic result, and actually we obtain two results. It's an array that gets returned of two symbolic results with a parameter c1. And that's already kind of alarming because it contradicts what I stated earlier, is that an equation of this type has a unique solution. So here we actually now see two solutions, And actually we have a parameter as well. But we haven't used all our data yet, so when we have a first order equation, we will always have a whole family of solutions depending on one parameter, and the parameter is then determined by the initial condition. So the initial condition has to be defined by a dictionary. So here we see the syntax. Capital D in a dictionary, and we have this arrow, this big arrow notation to link the key. The key here is the y, the function evaluated at the x naught, and then the value, the corresponding value to the key in the dictionary is the value y naught, here 5. Okay, and then the dsolve has to be applied again. So now do not forget that this is a keyword argument. ICS stands for the initial conditions. And then we have solved our problem. So we have one function, and that is the unique solution to the differential equation. Okay, this first initial introduction here serves to introduce the main constructions that we need to formulate a differential equation symbolically. Here in a Julia environment, but it's using SymPy, so the same almost works in, or the same, you will have the same result if you do this in Python. The syntax for dictionaries will be different. Okay, so what I would like to introduce next is the so-called scientific method. So we have a problem, and remember we have 3 problems to work through. We have a problem, 3 problems that we will translate into an ordinary differential equation. So there will be parameters in there that we will fix by imposing data. So the imposing of the data can also be a fitting process. So this is where the regression comes in handy again, which we have covered a while ago. So once we have the conditions for the parameters in there, then we can solve the ordinary differential equation. And then most importantly, we must interpret the result. Is our model a realistic model? If so, we are done. If not, we have to reconsider. All right, let's look at our first problem. So we are 13 minutes into this lecture. So this has some urgency here. How much time do we have for our speed to drop to 2 knots? Okay, first the equation. So we will apply Newton's rule. Newton's rule stating that the sum of all the inertial forces must equal the sum of all the external forces. So here in this model we have only one initial inertial force. That's the mass times the acceleration. And here we are interested in velocity. So it's important that we find immediately the right function that we want to solve for. So we want to know something about velocity. And velocity is a function of time. The derivative of the velocity is the acceleration. So the left-hand side in our ordinary differential equation is therefore set. So this is the inertial force, mass times acceleration. Then there is the water resistance, which is here modeled as proportional to the square of the velocity. The faster we go, the more resistance we observe from the water. So that's just a model, if you like, an assumption as well. And it so depends on some constant k. Okay. So our model is simple because we don't really have that much data. So that's also simple problems, simply stated problems often have good data. So here, notice that we don't really use the depth here. So that would be a more sophisticated model that somehow measures the pressure. But we are wasting time here. So let's continue. So formulating the ordinary differential equation, we have to define symbols not only for our independent variable, which is time here, but also for our constants, the mass and that constant k. Our function of interest is velocity v, and then we use the EQ construction to define the differential equation. We can simplify the model a little bit by lumping the mass and the constant k into one big constant, capital K. So the EQ construction has the advantage that we have an equation object as our ordinary differential equation, and we can select the left hand side and the right hand side. So what we would do by hand, if we would do this by paper and pencil, we would divide by m and then substitute the little k over m by the big K. But here you see this all now done symbolically for the equation. We selected the left hand side, right hand side, divided, and then did the substitution. And now we have a new left hand side, a new right hand side, and a new ordinary differential equation, which depends on one parameter, capital K. Okay, so that's our model. Now we have to solve it. And here we we recall that the initial velocity was 40 knots. So we set the initial condition at 40, and then we find an expression for the velocity. So the 40 actually comes in here as well. What is now this capital K constant? Because we still cannot do much with this expression. Well, we have to impose the data. So after 1 minute, the velocity has dropped to 30 knots. So we do the substitution to derive a new equation. So the new equation will then be an equation in K. So, and that we can solve. So we solve this equation for the capital K. So if we do solve, we have an array that's returned. So here I give the just the text-based verbatim output. But in the Jupyter notebook, you will see the large brackets. So that's an indication when you do the substitution. So we are working symbolically. So you can actually substitute any symbol by an array. But that already, the Jupyter notebook gave me a warning when I did this. So I want to point here that we select from that array the content. And now we have an expression that for the velocity that involves only the independent variable t. Okay, we're halfway this lecture. Can we solve the problem? So what now was the original question? So how long does it take? So we are asking for time, so we're going to solve an equation for time when the velocity falls below 2 knots. So we substitute the velocity, so the entire function is now replaced by the constant 2, and that will give us an equation that we solve for time, and that returns 57. So from the start of time, where we were happily cruising at 40 knots, it will take 57 minutes before the speed drops to 2 knots under our model. So we do have our crew. So this was done after we made the observation that the speed after 1 minute had dropped to 30 knots. So the crew still has 56 minutes left in this model to repair the reactor. Good. So this is our first problem, and we are halfway this lecture. 2 more problems to go. But let's first look at an exercise. So an invitation that also involves boats. And here it's more modeling exercise. Model the velocity, taking into account the resistance. So the resistance consists of 2 parts. We have a part that is proportional to the square of the velocity, and then another resistance that is proportional to the cube of the resistance. So it's a rowboat. So you may there's somebody in there rowing. So you can model. You have the constant of the velocity that will probably be constant. Then set up the differential equation and formulate conditions on the constants here. Okay, so now our second problem, which we can contemplate a little bit easier now springtime is coming. Winters can still be cold, so it can still be freezing. So don't let this problem be too trivial. So we are comfortably here at a temperature of 70 degrees when the furnace fails. So we must apply some cooling model. So it will be a first order model. So the change in temperature is proportional to the gradient that drives out the heat. So what is this gradient here? Well, we have the current temperature minus the outside temperature. So the outside temperature, which remains fixed at 20 degrees, and our current temperature that evolves. So the equation is then at the left the change in the temperature, so the derivative of the evolution of the temperature in function of time, and the right hand side is this difference, this gradient vector. So for some constant k here. So we have an initial condition, the initial temperature, and then we also have the condition that after 1 hour temperature has fallen to 65 degrees. So in a way this is a very similar model to the slowing down problem. So very similar, so we define a symbolic function. So this is done in the same session. So if you do this from scratch, you also have to define the symbol t. So we had already defined the symbol t, so now I'm not redoing this here. So we have the EQ construction that is applied to the formulation of the equation. and we set the initial condition. So we could already solve this without the initial condition, but let us apply the initial condition. Then we have the model, which is now here an exponential model. Okay, kind of a little bit surprising, but that means that we better obtain a negative value for k for this model to hold. You see the 20 that's coming in here. So the 20 is there as a constant. So what is k? Well, let us impose the data. So we recall that after 1 hour, the temperature has dropped to 65 degrees. So we will take our solution and substitute, replace the time t by 1 for 1 hour, and then replace the temperature. Now t at 1, so the substitution happens from left to right. So we will replace now the t of 1 by 65. And this gives us this model, the logarithm of 9 over 10, or 0.9. And if we take the decimal logarithms, yes, indeed, this will be negative. Good. So again, if we solve something, we obtain an array, so be sure then to select the content of this array. Alright, can we interpret this now numerically? So what is actually now the original problem? So we are working in a symbolic environment, so only at the very, very last minute we go to a floating point approximation. In the next lecture, we will reverse this. We will go to numerics pretty quick. So here, the original question was, when does it get to the freezing temperature inside? So for this, we take the solution we obtained. So it was stored in T-sol. And we replace the function, now t of t, big T of little t, we replace it by 32. And we find a symbolic solution, which is not so useful, unless you have a very good sense of how the logarithms work. Okay, it turns out when we compute a floating point approximation, which is just a simple conversion, taking the content of the vector, that we do have 13.5 hours before it starts to freezing. So it was in the evening when our furnace failed, so we still have 13 hours, so daylight will already be there. Okay, so we have solved our second problem, half hour in this lecture. Here is an equivalent exercise, but now we consider warming up. So we take a can of pop from the refrigerator, and we get kind of distracted and place it on it's placed on a counter for a while. Now we observe that after 2 minutes, the temperature of the can, so we hold a temperature gauge against it, and the temperature has dropped to 35. Has actually increased, increased by 1 degree Fahrenheit. So, what is the future evolution of the temperature of this can? When will the temperature reach room temperature? So this might seem a silly model, but sometimes you may have these indications of that some beverages need to be served at room temperature. So if you take them out of the fridge, say that you have a bottle of wine in the fridge that you need to serve at room temperature, how long do you need to wait? So this is an equivalent question. And some settings can be important to know. Or in some sense, indeed, also with the can of pop, nobody really wants to serve a can of pop at room temperature. Okay. Um, Another model. So far so good. We were always very good with our models. Our first attempt with our differential equation was always a success. It gave us a direct solution. Okay, so let us now consider an example where this is not the case. Let us predict the future population of a developed country. So life is good there, no catastrophes. And then it is realistic to assume that the bird growth, uh, the more people there are, the more birds there are. So it will be the change in the population will be proportional to the size. So this is our model. So we have at the left the change in the population. So the population size in function of time is our big P, and the independent variable is time. So we have at the left our differential, and at the right we have the size of the multiplication multiplied with some constant k. Sounds like a reasonable model. So let's solve it and formulate it. Again, t is already a variable in our setting. So we solve this differential equation after stating it with the EQ construction, and we find an exponential. Now the k is actually now positive. So because there is a positive relation to the size of the population and the change in the population. So it's actually not really realistic. So there are deaths that are happening. How unfortunate ever. So here is how we will consider a better model. So the deaths are the correction term. And we will assume that they are like in a Taylor series. So we have some function, and the function at the right, so the function that we are modeling is an unknown function, but it is proportional to the population size, and it's a function of the population size. Assume that we have that the dominating term is actually, let's focus on the birds. It's always a happy thing to happen. But then the second order term would then represent the correction term. So here, this is the capital K, where we subtract the second order term now. And that will give rise to what is called the logistics equation. So Taylor series are very good models. But it turns out that in terms of population, it actually makes sense. So it allows to make an interpretation. Okay, let us do some symbolic computation first. We will solve our logistic equation. So here we have the little k and the capital K. We still have the exponential in there, so we are probably not out of the woods here. But let's soldier on. So we have to interpret this model. Assume now, and we can always make that assumption, that whatever we measure our population with, let's say at the beginning of time that was 1. So if our population was, say, 1 million at the beginning of time, well, let's say that will be our 1. And that's in an attempt to get rid of some constants, and in particular the constant C1, which is an artifact of the fact that we always have a whole family of solutions for every first order, a family that depends on this parameter, which is here called C1. So let's get rid of the C1. Oops. There we go. So symbolic computation may always lead to expressions. Well, so here is how our result got simplified. But simplify, so there is simplifying and simplifying. SymPy also provides a simplify method. So as we stare on this result here, let us remember and let us use the simplify. And that indeed gives us a simplified model. So the C1 has disappeared. But we still have this exponential with the positive k, little k constant sitting in there. Not good. So let us make now a negative k exponent. And that can be done by dividing both numerator and denominator by this exponential, which by the way is never zero. So that then gives us a nice model. So this is the solution to this logistic equation with the two constants in. The little k is from the little people that come in, the birds. The capital K comes from the big people who leave. So the birds and the deaths. And now we see that if we look on the long term, so we are interested in the long term growth model of our population on the long term, and we are mathematicians, we let this time go to infinity, then the exponential dies off. So now actually we have exponential decay in the denominator, and our entire expression simplifies to this 2 ratio. So in some sense you still have, you could say you have one constant left. So you could simplify the k over k, the little k over the big K, as the carrying capacity. So that will be the limit. And that should be, since I took 1 as the initial condition, that should actually be here 1. Although you might actually, mathematically, you could have also steadily decaying towards that carrying capacity, which would be a very well, we are in a society that is developed, so we are not going into some problems here. But the carrying capacity would be, and I should probably draw something or have drawn something. So that's the horizontal asymptote. So our size of the population will never exceed the ratio little k over big K. So that's why this model, which is after all only a model, subject to all kinds of assumptions, which can be true or not true, this model is actually very fruitful, the logistic equation, for studying population growth, because it kind of leads to the notion, the acceptable notion, that there is a carrying capacity. So there is a limit to how large our population can grow. All right, is this now realistic? So here is a proposal for a topic for a third project. It can actually fit the topic of a second project. So one can hit 2 birds with 1 stone. A project that was earlier with regression was taking census data and fitting this census data with, say, a piecewise polynomial model. But here one considers explicitly the logistic model. And this also has to deal with prediction with regression. So what is the carrying capacity of the United States population? First, trying to see that the constants, little k and capital K, that you can get a good fit for that. But if you do, then so time 0 here is 1945. So what is the carrying capacity? One can ask questions, will the population of the United States ever reach 500 million? Would this be possible under this logistic model? Okay, in the last 10 minutes, or I may not need 10 minutes for this, let me introduce two mechanical models. And we will return to at least one of these models in the next lecture. So let's consider a pendulum. So that was our first example after the three problems. So, and here now I have a small picture. So we have a pendulum swinging on there's a mass and there is a length of a rod. And we want to know what is the angle of the deviation. So how do we model this? How do we get to the differential equation? Well, we can apply Newton's rule. So we have the inertial force that keeps the mass in place. So that's the mass times the acceleration. And the longer the rod here, the more heavier the force. So that's the left-hand side of our equation. So now we are interested in the deviation. So that's why our variable is actually the angle, and we have a second order differential equation. So in solving, then we will have to assume an initial position and an initial velocity. Typically that initial velocity is 0. The initial deviation is some angle. So we have the left-hand side, the mass times the acceleration, and then the vertical component of the gravitational force. With Newton's rule, we have the inertial force that has to equal the external force. So there is the gravitational pull, and the vertical component is expressed here, and that will be the right-hand side of this equation. You see, this model simplifies. The mass drops out. So there is an alternative model that applies the conservation of energy. So our pendulum in motion has kinetic energy, and there is also the gravitational force that provides the potential energy. So we compute the kinetic energy as related to the square of the velocity. And then the potential energy is computed from the gravitational force. So what is the model here in this conservation of energy? So we have that the sum of the kinetic and the potential energy equals some constant. So there's no energy added or removed in this model. And as an exercise, I ask you to apply symbolic computation to show that this equation is alternative, is just an equal valid alternative to the first equation derived with Newton's rule. So it has the velocity sitting in there. If we want to obtain the first equation, we need to get the acceleration. So the hint is to differentiate and then factor. You will get a more complicated equation. Now the derivative will simplify the right-hand side. It doesn't really matter what is the constant e here. So by taking the derivative, as the constant e is independent of time, that constant will drop out. So that's already one simplification. And you see actually now here that this model, if you look at the equation, also the mass can be factored out. Alright, here is then our other example. So I will return to this example in the next lecture. It will turns out that this leads to an equation that is very, very similar to the pendulum problem. So what do we have? We have here a fixed object. So this triangular here represents the wall, and we have attached to this wall a spring. And in this drawing here, the spring is all the way stretched out. So initially it was in equilibrium at position 0. So we have stretched, pulled the mass away. There is no friction here. So in a later model we will include damping. So we have the mass times acceleration. So we are interested in the position of this mass in as time evolves. So the x of t is the displacement from the equilibrium position. So it will also switch back and forth like the pendulum. That's why we essentially have the same equation, except that now for the right hand side, we have a much simpler model. We assume that the spring, the force from the spring, that is proportional to the displacement. So the spring, so springtime is coming. So the restoring force is directly proportional to the displacement, and this has this compensating factor. So in a way, we have this negative force. Okay, so this was a brief introduction to the scientific method using ordinary differential equations. So this lecture was entirely symbolic, which is convenient to formulate the equations, to solve the equations, imposing the data, and then also interpreting the results on problems that are sufficiently simple to state. So in this lecture I covered the first two sections of chapter 9 of our textbook, which is listed here. So in the next lecture we will take a more numerical turn. So we have already formulated one topic for a project. Is the logistic model really a good model for our United States population? The systems of the last problem will lead to a model of traffic flow. So you can imagine this damping of the spring, where the masses are now represented of the cars, and the springs actually are kind of the forces that are between the cars. So this will be a good model to study traffic flow, as I will try to explain in a future lecture, and that work can also be elaborated in a future topic for a project. So I hope this lecture was interesting, and I thank you for sitting through this lecture and watching it.